So we think we can see mutations even upstream of a transcription start site. So we haven't tried non-coding RNAs yet at this thing. When we've tried to put it in a completely dead region of the genome, transcriptionally I don't see any activity, so there probably is some requirement for at least accessibility. We don't really know yet how much transcription is required. Even at the promoter that I showed, where we can put a guy 3 kb transcription start, still see mutations. I can't guarantee you that there's zero transcriptional activity at that spot. There may be some transcription going in the opposite orientation. I would expect that non-coding RNA is transcribed, you'd have a decent chance of mutagenizing it, but we haven't tried it yet.
I'm hoping that I'm going to tell you something that's interesting, and of course I have this very biased view, which is I look at things from my computational lens. And are there any computer scientists in the room? I was anticipating not, but okay, there are. So there's one. Maybe every now and then I'll ask you a question. No, I'm just kidding. But so my goal here is going to be to basically actually just give you a flavor of what is machine learning. This is my expertise, and so just actually again to get a sense of who's in the room. Like if I picked on someone here, like raise your hand if you would be able to answer that question. Like what is machine learning? Okay, a handful. No, actually one or two. Great. Okay, so I just want to give you a sense of that, and I'm going to, most of this is going to be pretty intuitive. I'll try to make little bits of it concrete that I think will be helpful, and then I'll tell you how we used machine learning to improve guide design specifically for knockdown experiments. But I think a lot of it is probably useful for more than that, but we haven't sort of gone down that road, and so I can't say very much about that. And please interrupt me if something doesn't make sense or you have a question. I'd rather do that so everybody can kind of stay on board rather than it makes less and less sense the longer I go. Sorry. So machine learning actually during my PhD, one of the big flagship conferences was peaking at around 700 attendees, and when I go now it actually is capped, like it's sold out at 8,000 months in advance. So this field is just like taken off. Basically it's now lucrative for companies, and it's become a really central part of Google, Microsoft, Facebook, and all the big tech companies. So like this field has changed a lot, and kind of similar to CRISPR, there's an incredible amount of hype and buzz and ridiculous media coverage, and so it's a little bit funny, in fact, that I'm now working at these two kind of very hyped up areas. But anyway, so people in just the mainstream press now, you're always hearing about artificial intelligence and deep neural networks, and so these are like, so I would say machine learning is a sub-branch of artificial intelligence, and a deep neural network is sort of an instance of machine learning. And so like, what really is this thing? So it kind of overlaps sometimes with traditional statistics, but in terms of the machinery, but the goals are very different. But really, like the fundamental concept here is that we're going to sort of posit some model. So maybe like think linear regression is a super simple model, and you can like expose it to data that has some parameters, right, the weights, and then we essentially want to fit those weights. And that's the training. That's literally the machine learning. So I'm sorry if that sounds super simple and not like godlike, like machine learning and everything working magically, but that's really what it is. And right, and so let me just also give you like sort of drive home this point. So we're going to posit some sort of model, and so here I'm giving you the simplest example because I think most people here work with linear regression at some point in their life. And so you can think of this as a predictive model in the sense that if I give it a bunch of examples of y and x, and I learn the parameter beta, then for future examples where I don't have y, but I only have x, I can just compute x times beta and I get a prediction of y. So that's the sense in which I call this a predictive model, and that's very much how machine learning people tend to think of it, where statisticians are often very focused on what is beta, what are the confidence intervals around beta, and things like this. So like that's the sense in which there's a lot of overlap, but the goals are kind of quite different. We want to like use real data and make predictions, so here it's going to be predictions about guides, and which guides are effective at cutting and at knockout. Right, and three parameters, and we call these things that we put in here features. And so in the case of guide design, the question is going to be, what features are we going to put in there that allow us to make these kinds of predictions? So I'm going to get into that in a little bit, but just as an example, to make this concrete, it might be how many GCs are in this 30-mer guide plus context. Right, and like I said, we're going to give it some data, and so in this case, the data for guide design is going to be data from John Dent or others in the community that's now publicly available, where there are examples of, for example, what the guide was and how effective the knockout was, or what the cutting frequency was, for example. And I'm going to get a bunch of these examples, and then that's going to enable me to somehow find a good beta. And of course, we're not, actually we do sometimes use linear regression, but I'll tell you a little bit more about more sort of complex and richer models that let us do a lot more. And then the goal is going to be to fit this beta in a good way. And like I'm not going to do some deep dive on that here, but one way that you are probably familiar with is just mean squared error. And when you find the beta that minimizes this for your example training data, then you get some estimate beta, and you hope that on unseen examples, when you do x times beta, it gives you a good prediction. So that sort of make it somewhat concrete what I mean by a predictive model, and how you can view linear regression as a predictive model, and how you might use this for guide design. Okay, so obviously I'll tell you a lot more. So right, the linear regression is just sort of the simplest possible example. And so in our work, we actually use some of the time what are called classification or regression trees. And so in contrast to here, where you might have, say, you might have a bunch of these features, right? Like how many GCs were in my guide, and then another feature might be, was there an A in position 3? And you can put in as many as you want, and then you get all of these betas estimated. So it's very simple because in that case, none of these features can interact with each other, right? You just add x times beta 1 plus x times beta 2. So we call this like a linear additive model. In contrast, these trees allow very sort of deep interactions among the features. So this might be how many GCs. Of course, this is not suited to the features I just described, but this might be some feature like proportion of GCs, because now it's fractional. And then this algorithm, which is going to train the beta, so find a good value beta, will sort of through a procedure that I'm not going to go into detail for all these models how it works, but it's going to somehow look at the data and determine that it should first split on the second feature at this value, and then it will sort of keep going down that. So now partition the examples in my training data like this, and then on the second feature in this way, until you end up at the sort of leaves of this tree, and these leaves are the predictions. And so when you do it for the training data, whichever training examples here end up on this leaf, you basically take their mean, and that's now the prediction for that leaf. And if you take a new example, you basically just pipe it through these sort of rules, and you end up with that kind of prediction. It's simplified, but I think it's a good conceptual view. This is just another way of thinking about it. If you only had two features and you drew them like one against the other, then effectively every time you make a branch here, you're kind of cutting up the space. So that's also just another way to think about it. Whenever I give these talks, there's a bunch of young hungry students, and they just do deep neural networks. That's what everybody wants to do now. And so deep neural networks are kind of like a really fancy linear regression. So you could think of these as the x's in linear regression. You can think of this as imagine there's only one thing out here. I should have done a different picture. That's just y. And so this again is a mapping where you give it the x's, you do a bunch of stuff, and out you get a y here. Because linear regression, is a very simple thing, and now you can see there's all these other kinds of, we call these like hidden nodes, and so there's this complicated mess now of parameters, beta. And again, I'm not going to go into it. I just want to give you a sense that like linear regression is this very simple thing, and there's a lot of other models that let you do much, much better prediction, and these are typically the kind of models that we use because they're more powerful if we care about prediction. But the flip side is they're actually very hard to interpret, and so if you want to ask a question like, was it the GC feature, that is most important in your guide design, which is what always,
だから僕も今度はね、名刺を変えたんで、ね、同じあれなんだけど、別な名刺にしたんだ。はいはいはい、今度は、はい、今度光建設。光建設って有名じゃないですか。ね、ゼルも来るから。光建設ってよく私が知ってるあれかとか、ちょっと出てくる。はい、どうぞどうぞ。待っていいですか。いいですよ。はい、すいません。ちょっとよろしいですか。はい、どうぞどうぞ。いいですよ。これ現像のはもらえるようになってますんで、はい、そうですね。僕もこれ新しいやつ取ってまたご連絡しますから。今日はどうもありがとうございました。はい、 こ